Okay, we're going to take a look at differentiability. This means whether or not a derivative exists at a point. We say that if a function is differentiable, that means the derivative exists at every point in its domain. So we're going to take a look at 4 cases where the derivative does not exist. Okay, and we're going to focus on situations where the spot that it doesn't exist happens at x equals 0. First example is a corner, which we sometimes refer to as a sharp turn. So if we have a sharp turn, like we see with the absolute value of x function right here at the origin, if you have a sharp turn, the derivative does not exist. The reason it doesn't exist is because if you were to look at the one-sided derivatives, on the left side here you have a negative derivative, on the right side you have a positive. So as you get closer and closer to 0, they do not match up. Because you have that sharp turn, the derivative doesn't exist. Next situation is where we have what we call a cusp. If you were to graph y equals x raised to the 2/3 power, you would see what's called a cusp. This is where it comes down and kind of bends. It's very similar to our example up above where we have a sharp turn. So if we have a cusp, that's a situation where the derivative does not exist. Again, the idea is as you get closer and closer to that point on each side, the one-sided limits, the one-sided derivatives do not match up. Or in other words, the slopes of the tangent lines on each side do not match up. Let's look at y equals x raised to the 1/3 power. If we were to graph this and focus in on what's happening at the origin, my graph is not very good there, what you would see is that you have a vertical tangent line right there at x equals 0. So for a split moment, the slope of the tangent line is undefined. It's perfectly vertical. So the slope is undefined. If the slope is undefined, that means the derivative does not exist. Because remember, a derivative is a slope of the tangent line. So if you have a function such as x to the 1/3 power, where there's a part of it where it gets vertical for a split second, all right, where you would have a tangent line slope that is undefined, that's an indication that your function is not differentiable. Let's look at a situation here where we have a discontinuity. This is the last type of example where a derivative doesn't exist. And I'm going to add something to this. I wrote here a discontinuity such as a jump, comma, hole, or a vertical asymptote. So let's illustrate. So with the case of a jump, we're talking about the origin here. You might have a situation like this, or maybe you have an open circle there, and then a closed circle. Alright, so you have a jump. So in this example, the function is not continuous. And if it's not continuous, there's not going to be a derivative there. So in the case of a jump, there's no derivative at that point. In the case of a hole, so the function is going along, going along, going along, and then you have a hole. Okay? In that situation, again, it's discontinuous, therefore there's no derivative at that point. Okay? And lastly, you can have a vertical asymptote. So suppose we have a vertical asymptote right here. We can approach it from each side. Okay? Something like that. Another example of a discontinuity. So in general, if we have a discontinuity, there is no derivative that can exist at that point. So to summarize, differentiability implies continuity. So in other words, if a function has a derivative, it's going to be continuous. However, continuity does not always imply differentiability. Okay, just because a function is continuous doesn't mean it's guaranteed to have a derivative. Just look at our first three examples up above. All of these functions are continuous. All right, you can see up here we have continuous functions. However, there's spots where the derivative does not exist. Okay. So we could also conclude that if a function is not continuous, it can't be differentiable. Okay, so that's illustrated in our fourth case here where we have a discontinuity. Okay, so if it's not continuous, there's not going to be a derivative that exists.